What if the universe is built in such a way that no matter how hard you try, you can never know everything? Not because your tools are limited, not because your mind is too small, but because reality itself quietly refuses to give you complete answers. Tonight, we drift into one of the most unsettling and beautiful ideas ever discovered, Heisenberg's Uncertainty Principle. A principle that doesn't just describe physics, but redraws the boundary of knowledge itself. First, it sounds simple. The more precisely you know where something is, the less precisely you can know how it moves. And the more precisely you know how it moves, the more its position dissolves into uncertainty. But beneath that simple statement lies something far deeper, a quiet rule woven into the fabric of existence. If you've ever explored our Vellerin journey into the hidden nature of quantum reality, you may already sense where this is going. Because this idea doesn't stay confined to tiny particles. It reaches outward into atoms, stars, and even the limits of thought itself. And so tonight, we follow a question that has echoed through physics for nearly a century. Is uncertainty just a limitation, or is it the true shape of reality? As you settle in, let your mind slow down. Let the questions linger without needing immediate answers. And before we continue this quiet exploration, take a moment to subscribe to Vellerin's Sleepy Space Mysteries. Like the video, turn on the bell, and if you enjoy these journeys, consider becoming a member. And as always, tell me softly in the comments, where in the world are you listening from tonight? For most of human history, there was a quiet, comforting belief that the universe, no matter how vast or complex, was ultimately knowable. Not just partially, not approximately, but completely. Every motion, every force, every event unfolding according to precise rules that, if understood deeply enough, could reveal the entire story of existence from beginning to end. It is difficult to overstate how powerful this idea once felt. It shaped not only science, but the way humans understood their place in reality. The world was not a mystery to be lived in, but a system to be decoded. This vision reached its clearest form during the age of classical physics. In that world, objects behaved like perfectly obedient participants in a grand mechanical dance. A planet moved along its orbit with predictable precision. A falling object followed a path that could be calculated down to the smallest detail. Even light, once mysterious, became something that could be described through elegant equations. There was a sense that nature, at its core, was transparent, as if it were waiting patiently for the right mind to uncover its secrets. And then came a remarkable thought experiment, a quiet idea proposed by a mathematician named Pierre-Simon Laplace. He imagined a being, not a god but an intelligence, one that could, in a single moment, know the position and motion of every particle in the universe. Every atom, every grain of dust, every flicker of energy. For such an intelligence, nothing would be uncertain. The future would unfold before it as clearly as the present. The past would be just as accessible. There would be no mystery left, no unpredictability, no unknowns. Everything would be fixed within a perfect chain of cause and effect. This imagined entity became known as Laplace's demon. And while it was only a thought experiment, it captured the essence of the classical dream. If the universe truly operated like a perfect machine, then uncertainty was not real. It was only temporary, a gap in knowledge, problem waiting to be solved. At first glance, this idea feels almost reassuring. A universe where everything can, in principle, be known leaves no room for chaos or surprise. It suggests that beneath the surface of randomness lies a deeper order, that every storm, every decision, every event has a precise explanation, even if we do not yet see it. But if you sit with this idea for a moment, something begins to shift. Because a perfectly predictable universe is also a strangely quiet one. A place where nothing truly unexpected can happen. Where even the future is already written, waiting only to be revealed. And yet, for centuries, this was not seen as a limitation. It was seen as the ultimate goal of science, to remove uncertainty entirely, to replace mystery with clarity, to build a complete map of reality, where every question has an answer and every answer fits perfectly into place. Each new discovery seemed to bring that dream closer. Better telescopes revealed the motion of distant planets. More precise instruments measured time and distance with astonishing accuracy. Equations grew more refined, more powerful, more capable of describing the world in exact terms. But beneath this growing confidence, there were faint, almost invisible cracks. Subtle signs that the universe might not be as perfectly knowable as it seemed. In certain systems, tiny differences in starting conditions could lead to wildly different outcomes. In others, energy behaved in ways that resisted smooth, continuous description. These were not yet seen as fundamental problems. They were treated as technical challenges, complications that would eventually be resolved with better tools and deeper understanding. Still, the dream remained intact. The belief that, given enough time and knowledge, nothing would remain hidden. That uncertainty was not a feature of reality, but a flaw in human perception. A temporary blindness that science would one day cure. And it is here, at the height of this confidence, that our story begins to turn. Because as physicists started to look closer, not at planets or pendulums, but at the smallest building blocks of matter, something unexpected began to happen. The deeper they looked, the less the universe behaved like a machine. The rules that worked so beautifully at large scales began to falter. Particles did not follow clean, predictable paths. Light refused to act like a simple wave. Matter itself seemed to blur, to shift, to resist precise description. It was as if the closer we moved toward the foundation of reality, the more the foundation itself began to soften. Not collapse, but change character. And slowly, almost reluctantly, a new possibility began to emerge. What if uncertainty was not something to be eliminated? What if it was not a problem at all? What if it was part of the design? This question did not arrive all at once. It unfolded gradually, through experiments that refused to match expectations and theories that challenged deeply held assumptions. But at its heart, it pointed toward something radical. the idea that the universe might not allow perfect knowledge, not because we lack the tools, but because such knowledge simply does not exist in the way we imagined. And as we move forward, this quiet shift will become impossible to ignore, because the classical dream, the dream of total certainty, is about to meet a boundary it cannot cross. As the confidence of classical physics reached its peak, something subtle began to unfold beneath the surface, a quiet tension between what the equations predicted and what experiments were beginning to reveal. At first, these inconsistencies were easy to dismiss. After all, science had always progressed by resolving small mismatches between theory and observation. But this time, the mismatches did not behave like ordinary problems. They lingered, they deepened, and slowly, they began to suggest that the issue was not with the measurements, but with the very assumptions underlying the classical dream. One of the earliest signs appeared in the study of heat and light. Physicists were trying to understand how objects emit radiation when they are heated, something as simple as a glowing piece of metal or the warmth radiating from a star. According to classical theory, energy should be distributed smoothly across all possible frequencies of light. But when the calculations were carried out, the results led to an impossible conclusion. At higher frequencies, the predicted energy output grew without limit, diverging toward infinity. This contradiction became known as the ultraviolet catastrophe, a name that quietly hinted at how serious the problem truly was. Yet the real mystery was not the failure itself, but the fact that reality refused to follow the prediction. Experiments showed that the energy did not diverge. Instead, it followed a very specific curve, one that classical physics simply could not explain. It was as if nature itself was quietly ignoring the rules that had worked so well everywhere else. To resolve this, a physicist named Max Planck made a cautious, almost reluctant proposal. He suggested that energy might not be continuous after all. Instead of flowing smoothly, it might come in tiny, discrete packets. These packets, later called quanta, set a minimum unit below which energy could not be divided. Planck did not fully believe this idea at first. To him, it was a mathematical trick, a way to make the equations fit the data. But the results were undeniable. The curve matched perfectly, and with that small adjustment, something profound had changed. The universe, which had once been imagined as infinitely divisible and perfectly smooth, now showed signs of being granular at its core. Not continuous, but step-like. Not infinitely precise, but built from fundamental units. Soon after, another puzzle emerged. When light struck certain metals, it could eject electrons from their surface, a phenomenon known as the photoelectric effect. Classical theory predicted that the energy of these electrons should depend on the intensity of the light, and that weaker light would take time to accumulate enough energy to release them. But experiments told a different story. The electrons were emitted instantly, and their energy depended not on the intensity, but on the frequency of the light. It did not matter how bright the light was. If the frequency was too low, nothing happened. This result made little sense within the classical framework. But Albert Einstein offered a bold explanation. He proposed that light itself was quantized, composed of discrete packets of energy, later called photons. Each photon carried a specific amount of energy tied directly to its frequency. If the energy was high enough, it could eject an electron immediately. If not, no amount of brightness could compensate. With this, the strange idea of quantization extended beyond matter into light itself. The boundary between waves and particles began to blur. Light behaved like both, depending on how you looked at it. And this dual nature was not just a curiosity. It hinted at a deeper structure, one that did not fit neatly into the categories that classical physics had relied upon for centuries. At this stage, the cracks in the classical dream were no longer isolated. They were spreading. Each new experiment added another layer of tension. Electrons, once thought to be tiny particles orbiting atoms like planets around a star, began to exhibit wave-like behavior. They could interfere with themselves, producing patterns that should only be possible for waves. Yet when observed in other contexts, they behaved like localized particles. It was as if the fundamental building blocks of reality refused to choose a single identity. Not fully particles, not fully waves, something in between, something that challenged the very language used to describe them. And beneath all of this, a deeper question began to form. If matter and energy do not behave in strictly predictable, continuous ways, then what does it mean to know their properties? Can we still speak of exact positions, exact velocities, exact states, in the way classical physics assumed? At first, physicists tried to preserve the old framework. They introduced hybrid models, combining classical ideas with new quantum rules. One of the most famous was the model of the atom proposed by Niels Bohr, where electrons orbited the nucleus but were restricted to specific energy levels. It worked surprisingly well for certain cases, explaining the spectral lines of hydrogen with remarkable accuracy. But it was not a complete solution. It felt temporary, like scaffolding built around a structure that had yet to be fully understood. And so the tension remained, a growing sense that the classical dream of perfect knowledge, the idea that everything could be known with unlimited precision, might not survive the transition into this new quantum world. As we continue, this tension will reach a breaking point, because the question is no longer just how particles behave, but what it even means to describe them. And in that shift, we begin to approach the moment when uncertainty will no longer be seen as a flaw, but as a fundamental rule. As the strange behavior of light and matter continued to unfold, physicists found themselves standing between two worlds, one familiar and predictable, the other uncertain and deeply unfamiliar. The old language of classical physics still worked beautifully for planets, machines, and everyday motion. But at the atomic scale, that language began to lose its meaning. Words like path, orbit, and even position started to feel less like descriptions and more like assumptions that no longer applied. One of the most unsettling discoveries came from experiments that revealed something almost impossible to reconcile with classical thinking. Particles, when not observed too closely, could behave like waves. They could spread out, overlap, and interfere with themselves. This was not metaphorical. It was measurable. Patterns appeared on detection screens that could only be explained if each particle was not traveling along a single definite path, but instead exploring many possibilities at once. And yet, when scientists tried to pin these particles down, to observe their exact path or location, the wave-like behavior vanished. The interference patterns disappeared. The particles seemed to choose a single outcome. It was as if the act of asking a precise question forced reality into a more definite form, but at the cost of losing something else. This created a growing sense of tension, because classical physics depended on the idea that objects always have well-defined properties, whether we measure them or not. A particle should have a position and a velocity at every moment. Even if we do not know those values, they should still exist, waiting to be discovered. But these new experiments suggested something far stranger, that certain properties might not exist in a definite way until they are measured. And even then, defining one property precisely seemed to make another less certain. At first, this idea was resisted. It felt too radical, too disruptive. Physicists attempted to preserve as much of the classical picture as possible, building models that blended old intuition with new observations. But these models grew increasingly strained. They worked in some cases, failed in others, and often required rules that felt arbitrary, as if they were being forced to fit a reality that refused to cooperate. The deeper scientists looked, the more it became clear that something fundamental had to change. Not just the equations, but the way reality itself was described. And slowly, a new kind of framework began to take shape. One that did not rely on precise trajectories or fully determined states. Instead, it described systems in terms of possibilities, not what a particle is doing at a specific moment, but what it might do when observed. In this emerging view, a particle is not a tiny object moving along a fixed path. It is better understood as a set of potential outcomes, each with a certain likelihood. These possibilities evolve over time, guided by mathematical rules that are precise, but not deterministic in the classical sense. The outcome of a single event cannot be predicted with certainty. Only the probabilities can be known. This shift was subtle but profound. It did not mean that the universe had become chaotic or lawless. On the contrary, the new theory was extraordinarily precise in its predictions. But the precision applied to probabilities, not to individual events. The certainty of classical physics was replaced by a different kind of clarity, one that acknowledged limits not as failures, but as inherent features of the system. And within this new framework, a quiet pattern began to emerge. Whenever physicists tried to define certain pairs of properties with increasing precision, they encountered a trade-off. Improving the accuracy of one seemed to degrade the accuracy of the other. This was not due to poor measurement techniques. It appeared even in the most carefully controlled experiments. It was consistent, repeatable, and deeply embedded in the mathematics of the theory. At first, this trade-off was seen as a curiosity, a pattern that might have a deeper explanation. But as the theory developed, it became clear that this was not a side effect. It was a central feature, a rule that governed how certain aspects of reality were connected. And here we begin to approach something essential. because this trade-off is not just about particles or experiments. It speaks to the structure of knowledge itself. It suggests that some aspects of reality are linked in such a way that sharpening one necessarily blurs the other. Not because we are interfering with the system, but because the system does not allow both to be sharply defined at the same time. This idea is subtle and it can feel counterintuitive. We are used to thinking that more precision is always better, that with enough care, enough refinement, we can approach perfect knowledge. But this emerging pattern hints at something different, that there may be a boundary not imposed by technology or human limitation, but by the nature of reality itself. And as this realization slowly took hold, one physicist in particular began to see it more clearly than anyone else. He started to strip away the old assumptions, to rebuild the theory using only what could be directly connected to observation. And in doing so, he uncovered a principle simple in form, but profound in its implications. A principle that would reveal once and for all that the dream of perfect knowledge was not just difficult, but impossible. By the mid-1920s, the tension between the old classical worldview and the emerging quantum reality could no longer be ignored. The pieces were all there, scattered across experiments, equations, and strange observations that refused to fit together neatly. What was missing was not data, but a new way of thinking, a framework that did not try to force reality back into familiar shapes, but instead accepted that those shapes might have been incomplete from the very beginning. It was in this atmosphere that a young physicist began to approach the problem from a different angle. Instead of trying to describe what electrons were doing in terms of orbits or trajectories, he asked a simpler, more radical question. What if we only talk about what can actually be observed? Not imagined paths, not hidden motions, but measurable quantities. Frequencies of light, intensities, transitions between states, things that experiments could directly confirm. This shift might seem subtle, but it carried enormous consequences. Because the moment you remove unobservable assumptions, much of the classical picture begins to dissolve. The idea of an electron circling a nucleus like a tiny planet gone. The notion of a perfectly defined path through space, no longer necessary. What remains is something more abstract, but also more honest. A description built entirely from relationships between measurable outcomes. As this new approach developed, something unexpected emerged from the mathematics. The quantities used to describe physical systems did not behave like ordinary numbers. The order in which you combined them began to matter. Performing one operation before another produced a different result than doing them in reverse. This was not just a mathematical curiosity. It hinted at a deeper structure, one in which certain properties were fundamentally linked in a way that prevented them from being simultaneously exact. At first, this behavior seemed strange, even inconvenient. But the more closely it was examined, the more it revealed a consistent pattern. Certain pairs of quantities were connected through this non-interchangeable relationship. And whenever such a pair appeared, the same limitation followed. You could refine one quantity, but only at the expense of the other. This was not a technical issue. It was not something that could be fixed with better instruments or more careful experiments. It was embedded in the very framework being built. A structural feature as unavoidable as the rules of arithmetic or the logic of geometry. And slowly the realization began to settle in. The trade-off that had appeared in earlier experiments, the one that linked precision in one measurement to uncertainty in another, was not an accident. It was a reflection of this deeper mathematical structure, a sign that the limits observed in the laboratory were echoes of something more fundamental. To understand this intuitively, imagine trying to describe something that is both perfectly localized and perfectly smooth at the same time. The more tightly you confine it in one sense, the more it must spread in another. This is not a flaw in description. It is a property of how certain forms of information are connected. And in the quantum world, this connection is not optional. It is built into the way reality is expressed. At this point, the classical dream begins to unravel completely, because that dream depends on the idea that every property of a system can, in principle, be defined with arbitrary precision at the same time. That position, velocity, energy, and every other measurable quantity exist as exact values, waiting to be discovered. But the emerging framework tells a different story. It suggests that some of these quantities are not independent in that way, that they are bound together by relationships that impose limits on how precisely they can coexist. This is the moment where uncertainty stops being a temporary inconvenience and becomes something deeper, not a gap in knowledge, but a boundary on what knowledge can be. A line that cannot be crossed, no matter how advanced the technology or how refined the method. And yet, this realization does not make the universe chaotic or unknowable. Quite the opposite. It introduces a new kind of order, one where limits are not failures, but guiding principles, where understanding comes not from eliminating uncertainty, but from recognizing how it is structured. In this new view, the goal of science shifts subtly. It is no longer about achieving perfect precision in every aspect of a system. Instead, it becomes about choosing what to know and understanding the cost of that choice. Because every measurement, every observation is also a selection, a decision about which aspect of reality to bring into focus and which aspect to allow to blur. And as this idea takes shape, it prepares the ground for a single clear statement, a principle that will capture this entire shift in one elegant expression. A principle that does not describe a specific experiment or system, but applies to the fabric of reality itself. A principle that will reveal with quiet certainty that the universe does not permit everything to be known at once. And then, almost quietly, the idea that had been forming beneath all these discoveries finally took shape. Not as a vague suspicion, not as a pattern hidden in equations, but as a clear and unavoidable statement about reality itself. A realization that would not only reshape physics, but redefine what it means to know anything at all. Up to this point, the classical dream had still lingered in the background. Even as strange results accumulated, there remained a hope that a deeper theory might restore certainty, that perhaps the unpredictability and trade-offs were only temporary symptoms of an incomplete understanding. But now that hope began to fade, because the emerging framework did not merely suggest limitations, it required them. At the heart of this shift was a simple but profound insight. The properties we use to describe the world are not always independent. They are connected in ways that place limits on how precisely they can be defined together. This is not because we lack skill or precision. It is because the very structure of reality does not allow all aspects to exist in perfectly sharp form at the same time. This idea is subtle, and it unfolds slowly when you sit with it. Imagine trying to describe a system completely. Every detail, every motion, every position, every change. In the classical view, this is always possible in principle. There is nothing stopping you except practical limitations. But in the quantum view, something deeper intervenes. The act of defining one aspect of the system with extreme clarity changes what can be said about another aspect. Not as a side effect, but as a direct consequence of how those aspects are related. This means that knowledge itself has a structure. It is not just a collection of facts waiting to be gathered. It is shaped by relationships, by constraints, by boundaries that define what can be known together and what cannot. And once you begin to see this, the classical dream of perfect knowledge starts to feel less like an achievable goal and more like a misunderstanding. Because the dream assumes that reality contains a complete set of exact values, fully determined and simply waiting to be uncovered. But what if that assumption is wrong? What if, at the deepest level, reality does not store information in that way? What if certain details do not exist simultaneously in the precise form we expect? This is the quiet revolution that now takes hold. A shift from thinking of the universe as a fixed collection of properties to seeing it as a system of relationships and possibilities. A place where what can be said depends not only on the system itself, but on how we choose to interact with it. And yet, this is not a descent into confusion or ambiguity. The new framework remains incredibly precise, predicts outcomes with astonishing accuracy. It allows scientists to calculate probabilities, design experiments, and build technologies that rely on quantum effects. But it does so within a different kind of order, one where certainty is replaced by balance, where precision in one direction is matched by uncertainty in another. As this understanding deepens, something unexpected happens. The idea of uncertainty begins to lose its negative connotation. It is no longer seen as ignorance or imperfection. Instead, it becomes a feature, a defining characteristic of how reality is organized. A guide that tells us where clarity is possible and where it must give way to openness. This is a subtle but important shift in perspective, because it changes how we relate to knowledge itself. Instead of trying to eliminate uncertainty, we begin to work with it, to understand its structure, to use it as a tool, to recognize that it is not something to overcome, but something to navigate. And in this way, the boundary that once seemed like a limitation becomes something else entirely. A kind of map, a way of understanding how different aspects of reality connect, how they influence each other, and how our attempts to describe them are shaped by those connections. Looking back, the classical dream still holds a certain beauty. The idea of a perfectly knowable universe is elegant, reassuring, and deeply intuitive. But it is also, in a sense, incomplete. It captures only one way of seeing the world, one that works at large scales, but begins to break down as we move closer to the foundations of existence. What replaces it is not chaos, but something more nuanced. A universe that is lawful, structured, and deeply coherent, but not fully transparent. A universe that allows us to know a great deal, but not everything at once. A universe where mystery is not an obstacle, but part of the design. And as we come to the end of this part, we can begin to feel the full weight of that realization. The dream of perfect knowledge has not simply been challenged. It has been transformed, replaced by a deeper understanding of what knowledge means and what its limits truly are. In the next part, we will step directly into the heart of this transformation. We will explore the principle itself, the one that gives this idea its most precise and powerful expression. And as we do, we will see that uncertainty is not just a philosophical concept, but a measurable, testable, and fundamental feature of reality. For now, let the thought settle gently, that the universe, in all its vastness, is not something that can be fully captured in a single, perfect description. That some edges will always remain soft, not because we have failed to sharpen them, but because they were never meant to be sharp. And if you are still here, still drifting through these quiet ideas with me, let me know by softly writing the number 1 in the comments. And now we arrive at the moment where everything changes, not gradually, not subtly, but with a clarity that reshapes the very meaning of reality. All the tensions we have followed, the strange behavior of light, the dual nature of matter, the quiet breakdown of classical certainty, begin to converge into a single insight. An idea that does not merely describe the quantum world, but defines its limits. Heisenberg's Uncertainty Principle. At first, it sounds almost too simple to carry such weight. The more precisely you know the position of a particle, the less precisely you can know its momentum. And the more precisely you know its momentum, the less precisely you can know its position. A trade-off, a balance, a limit that cannot be overcome. But this is not just a statement about measurement. It is not a warning about clumsy experiments or imperfect tools. It is something far deeper, a declaration that these two properties, position and motion, do not exist together in perfectly sharp form, not hidden, not waiting to be discovered, but fundamentally undefined beyond a certain point. To feel the depth of this, we have to let go of a familiar assumption, the idea that every object carries a complete set of properties at all times, that even if we do not measure them, those properties still exist in exact form. This assumption is so natural that it rarely feels like an assumption at all. Feels like common sense. But the uncertainty principle quietly removes it. It tells us that if we prepare a particle so that its position is extremely well defined, tightly localized in space, then its momentum becomes spread out across a range of possibilities. Not because we disturbed it, not because we lack precision, but because a state with both perfectly sharp position and perfectly sharp momentum simply does not exist. This is the first major shift. Reality is not hiding information from us. It is not withholding details that could, in principle, be revealed. Instead, it is structured in such a way that certain combinations of properties are never simultaneously exact. The limit is not in our knowledge, but in the nature of what can be known. To make this more intuitive, imagine trying to describe a sound. A very short, sharp sound, like a quick tap, is well defined in time. You know exactly when it happens, but it contains a wide range of frequencies. It is not a pure tone. On the other hand, a perfectly pure tone, a single frequency, must extend over a long period of time, cannot be confined to a precise instant. The more you localize it in time, the more its frequency spreads. The more you define its frequency, the less precise its timing becomes. This is not a flaw in sound. It is a property of waves. And in the quantum world, particles behave in ways that are deeply connected to this kind of structure. They are not just points moving through space. They are described by something more like a spread-out pattern of possibilities. And because of this, the same kind of trade-off appears. Localization in one aspect leads to spreading in another. But here is where the principle becomes truly profound. It is not limited to sound or even to waves in the classical sense. It is embedded in the mathematical framework that describes all quantum systems. It applies not only to position and momentum, but to other pairs of properties as well. Energy and time, different directions of motion, any pair that is linked in this deeper way. And in each case, the message is the same. There is a lower bound to how precisely both can be known together. A minimum uncertainty that cannot be reduced, no matter how perfect the experiment. At this point, the classical dream of perfect knowledge fully dissolves. Because even in principle, even with infinite precision and perfect control, there is no way to define all aspects of a system with unlimited accuracy. The universe does not permit it, and yet, this does not make the world vague or chaotic. The uncertainty principle is exact. It gives a precise limit. It tells us exactly how much uncertainty must exist. It replaces the idea of complete certainty with a different kind of structure, one where limits are part of the law. This is why the principle feels both unsettling and strangely elegant. It removes something we thought we could have, perfect knowledge, but replaces it with something deeper. A framework that tells us not only what we can know, but how knowledge itself is shaped. And as we move forward, we will begin to see that this principle is not just an abstract rule. It has real consequences. It explains why atoms do not collapse, why matter has structure, why the universe, at every scale, maintains a balance between what is defined and what remains open. But before we explore those consequences, there is still one question lingering quietly beneath the surface. A question that has followed us from the beginning. If uncertainty is not caused by measurement, then what is it really telling us about reality? To understand what uncertainty is truly telling us about reality, we have to move one step deeper, beyond experiments, beyond thought experiments, and into the quiet structure that sits underneath them all. because what Heisenberg uncovered was not just a pattern in observations, but a feature embedded in the very language used to describe the quantum world. And once you begin to see that structure, the mystery starts to shift from something confusing into something almost inevitable. In classical physics, describing a system is straightforward. You assign numbers to properties: position, a velocity, an energy. These numbers behave in familiar ways. You can combine them, rearrange them, and the order does not matter. 2 plus 3 is the same as 3 plus 2. Measuring position and then velocity gives the same result as measuring velocity and then position, at least in principle. The world is built from quantities that can coexist without interfering with each other. But in the quantum world, this simplicity quietly breaks down. The properties we use to describe systems are no longer just numbers. They behave more like operations, actions that extract information from a system. And crucially, the order of these operations begins to matter. If you try to determine one property first and then another, you may not get the same outcome as if you reverse the order. This is not a flaw or an inconvenience. It is a signal, a sign that these properties are not independent in the way we once believed. They are intertwined, connected by a deeper structure that does not allow them to be simultaneously fixed with perfect clarity. And from this structure, the uncertainty principle emerges naturally, not as an added rule, not as a correction, but as a direct consequence of how these properties relate to each other. It is as if the fabric of reality itself enforces a kind of balance, a rule that says you may sharpen one aspect, but only by allowing another to soften. To make this feel more intuitive, return for a moment to the idea of waves. When you describe a wave, you can focus on where it is or on how it moves. But these two descriptions are connected. A wave that is tightly confined in space cannot have a single, well-defined motion. It must contain a range of possibilities. And a wave that has a perfectly defined motion must extend broadly through space. This is not a limitation of measurement. It is a property of how waves exist. In quantum mechanics, particles inherit this same structure. They are described by patterns that carry information about where they might be and how they might move. And because of this, the same trade-off applies. It is not something imposed from the outside. It is built into the way these patterns are formed. This is why the uncertainty principle does not depend on observation. Even before any measurement is made, the system itself carries these spreads, these ranges of possibility. Measurement does not create the uncertainty. It reveals it. And this brings us back to a subtle but important shift in perspective. In classical thinking, uncertainty comes from ignorance. We do not know something because we have not measured it precisely enough. But in the quantum world, uncertainty is not about what we fail to know. It is about what cannot be known in a combined way. It is a feature of the state itself, not a gap in our understanding. This distinction changes everything, because it means that reality is not composed of perfectly sharp facts hidden beneath layers of noise. Instead, it is composed of relationships that define how sharply certain aspects can exist together. The sharpness itself is limited not by us, but by the structure of the system. And once you accept this, a new kind of clarity begins to emerge. The uncertainty principle is not telling us that the universe is vague. It is telling us that precision has a shape, that knowledge is not unlimited in all directions at once, but must be distributed across different aspects of reality. You can concentrate it here or there, but not everywhere simultaneously. This is why physicists no longer see uncertainty as a problem to be solved. Instead, it becomes a tool, a guide for understanding how systems behave, how measurements should be designed, how information flows through the quantum world. It tells you where precision can be gained and where it must be given up. And in that sense, it becomes part of the grammar of physics, a rule that shapes every sentence we write about the universe. But even with this understanding, something remains quietly profound. Because if the properties of reality are structured in this way, then the idea of a fully detailed, perfectly defined universe, a universe where every quantity has an exact value at every moment, begins to feel less like a hidden truth and more like a story we once told ourselves. A useful story, perhaps, but not the final one. And so the question returns, now with greater clarity than before. If the universe is not built from perfectly sharp facts, then what is it built from? What is the true nature of a system that cannot be fully pinned down, no matter how carefully we look? As we continue, we will begin to see that this question leads us beyond physics, into something deeper, into a view of reality not as a fixed set of answers, but as a landscape of possibilities, shaped by the very act of asking. If reality is not built from perfectly fixed properties, then what takes their place is something far more subtle, a structure made not of certainties but of possibilities. And this is where the uncertainty principle begins to reveal its deeper meaning, because it is not simply limiting what we can know. It is quietly telling us what a physical system actually is. In the classical view, a system is like a snapshot. At any given moment, every detail exists in a definite state. Position, motion, energy, all precisely defined, even if hidden from us. But in the quantum world, this idea gives way to something more fluid. A system is no longer a fixed collection of exact values. Instead, it becomes a kind of spread, a range of potential outcomes, each with its own likelihood. And this spread is not just a reflection of ignorance. It is the most complete description possible. It is what the system truly is. When you prepare a particle in a certain way, you are not assigning it a single position or a single momentum. You are shaping a distribution, a pattern that tells you where it might be found and how it might behave when measured. And because of the uncertainty principle, this pattern cannot be made arbitrarily sharp in all directions at once. It has a kind of built-in width, a minimum blur that cannot be removed. This blur is not a flaw. It is a signature, a mark of the quantum nature of reality. To picture this, imagine not a point, but a cloud, a soft, shifting region where the particle is not located at a single exact spot, but has a higher likelihood of being found in some places than others. The cloud can be made tighter, more concentrated, but only by allowing it to spread in another way. If you compress it in space, it expands in motion. If you narrow its motion, it spreads out in space. The balance is unavoidable, and within this balance lies a quiet stability, because this spreading is not random. It follows precise rules. The shape of the cloud evolves in time according to well-defined patterns. The probabilities change in predictable ways. And when measurements are made, the outcomes align exactly with those probabilities. The uncertainty is not chaos. It is structured openness. This perspective helps resolve a question that has lingered beneath the surface. Why does the act of measurement seem to change the behavior of a system? Why does observing a particle sometimes destroy its wave-like properties? The answer is not that observation creates reality in a mystical sense. It is that measurement selects from the range of possibilities encoded in the system. Before measurement, the system contains multiple potential outcomes. After measurement, one of those outcomes is realized. But the underlying spread, the set of possibilities, is always governed by the same rules, including the limits imposed by uncertainty. And this brings us back to the core idea in a new light. The uncertainty principle is not just about what we cannot know. It is about how reality is organized before we know anything at all. It tells us that the world at its most fundamental level is not a collection of fixed facts, but a structure of potentialities. And these potentialities are not arbitrary. They are constrained, shaped, and balanced by relationships that define how sharply different aspects can coexist. This is why attempts to imagine hidden variables, exact values that exist but are simply concealed, run into difficulty. Because the uncertainty principle is not about missing information. It is about the absence of simultaneous exactness itself. It is not that the values are hidden. It is that they are not jointly defined in the way classical intuition expects. This realization can feel unsettling at first. It challenges the idea that there is a single, complete description of reality waiting to be uncovered. Instead, it suggests that any description is inherently partial, shaped by the way we choose to engage with the system. But at the same time, it opens up a deeper kind of understanding, because it reveals that the limits of knowledge are not arbitrary. They are meaningful. They reflect the structure of the world itself. And in that sense, uncertainty becomes a kind of guide. It tells us how to think about systems, how to frame questions, how to interpret results. It becomes part of the foundation, not something that stands in the way of it. As physicists learned to work within this framework, they began to see that the uncertainty principle was not an obstacle, but a key. It explained why atoms have stable sizes, why particles do not collapse into single points, why matter has structure at all. Without this built-in spread, the universe would look very different, perhaps not capable of supporting the complexity we observe. And so, what began as a limit, a restriction on what can be known, transforms into something else entirely. A principle that makes the structure of reality possible. A rule that ensures balance between localization and motion, between definition and openness. And as we continue, we will begin to see how this balance extends far beyond individual particles, shaping everything from the smallest atoms to the largest structures in the cosmos, quietly maintaining the delicate equilibrium that allows the universe to exist as it does. There is a moment when you sit quietly with the uncertainty principle long enough where it begins to feel less like a scientific rule and more like a boundary line drawn gently across reality itself. Not a harsh barrier, not something that blocks understanding, but something that defines its shape. And once you begin to see that boundary clearly, you start to notice it everywhere, not only in abstract theory, but in the very stability of the world around you. Consider something as simple as an atom. In the classical picture, it should not exist in any stable form at all. An electron carrying electric charge, orbiting a nucleus, should continuously radiate energy. And as it loses that energy, it should spiral inward, collapsing into the nucleus in a fraction of a second. Matter, as we know it, should be impossible. And yet, atoms are stable. They persist. They form the foundation of everything we see. The reason for this stability lies quietly within the uncertainty principle. If you try to confine an electron very tightly near the nucleus, forcing its position into a very small region, the uncertainty in its motion becomes enormous. Its momentum spreads out, and with that spread comes an increase in its kinetic energy. This increase acts like a kind of resistance, preventing the electron from collapsing inward. The tighter you try to squeeze it, the more it pushes back. And so a balance is formed. Not a rigid orbit, not a fixed path, but a stable region where the electron exists as a cloud of probability. A place where attraction and uncertainty meet, creating structure instead of collapse. This same principle echoes outward into larger systems. In solids, for example, electrons do not simply pile into the lowest possible state. They spread out across a range of energies, filling what physicists call bands. This distribution is not arbitrary. It is shaped by the same underlying limits. Confining many particles within a finite space forces their possible motions to spread, generating an effective pressure that resists further compression. Even the firmness of matter, the fact that objects do not pass through each other, is tied in part to this quantum resistance. And if we follow this thread even further, we find it reaching into the cosmos itself. In the dense remnants of stars, where gravity attempts to crush matter into ever smaller volumes, the uncertainty principle again steps in. As particles are forced closer together, their motion becomes increasingly uncertain, and their energy rises. This creates a pressure that can counteract the immense pull of gravity. In white dwarf stars, it is the electrons that provide this support. In neutron stars, it is the neutrons themselves. Without this quantum pressure, these stars would collapse further, perhaps disappearing entirely into black holes. So the same principle that governs the behavior of a single particle also determines the fate of entire stars. It is not confined to the microscopic world. It is woven into the structure of the universe at every scale. And yet, despite its reach, the uncertainty principle remains deeply misunderstood. It is often described as if it were simply about measurement, as if observing a system disturbs it and creates uncertainty. But by now, we can see that this is only a surface-level interpretation. The uncertainty is already there, built into the state of the system before any measurement takes place. Observation does not create the limit. It reveals it. This distinction is important because it shifts the focus away from the observer and back onto the nature of reality itself. The universe does not become uncertain because we look at it. It is structured in such a way that certain combinations of properties are never simultaneously sharp, whether we observe them or not. This realization also helps resolve a deeper philosophical tension. For a long time, uncertainty was associated with imperfection, a sign that something was missing from our understanding. But in the quantum framework, uncertainty is not a gap. It is a feature, a necessary ingredient in the architecture of reality. Without it, atoms would collapse, matter would lose its structure, and the delicate balance that allows complexity to emerge would be lost. So what appears at first as a limitation reveals itself as a kind of protection, a rule that prevents extremes, that maintains balance, that ensures stability across scales. It is not an obstacle to knowledge, but a condition that makes knowledge meaningful, because it tells us that precision is not absolute. It is contextual. It depends on what we choose to focus on and what we are willing to let remain open. And in this way, the uncertainty principle becomes more than a scientific statement. It becomes a lens through which we can see the universe differently, not as a rigid machine with perfectly defined parts, but as a dynamic system where definition and openness coexist, where clarity is always paired with a kind of softness at the edges. As we move toward the final segment of this part, one question remains, and it is perhaps the most quietly profound of all. If uncertainty is woven into the structure of reality, if it shapes everything from atoms to stars, then what does that mean for our search for ultimate truth? Is there a final, complete description waiting somewhere beyond our reach? Or is the very idea of completeness something we must learn to let go of? As we reach the final stretch of this part, the uncertainty principle begins to settle into something deeper than a scientific idea. It becomes a quiet challenge to how we think about truth itself. Because for centuries, the pursuit of knowledge was guided by a simple belief that somewhere beneath complexity, beneath noise, beneath limitation, there exists a perfectly complete description of reality, a final answer, a set of exact values that, if uncovered, would leave nothing unknown. But now that belief begins to soften, not because science has failed, but because it has succeeded in revealing something unexpected, that the universe may not be built to support such completeness in the way we imagined. The uncertainty principle does not say that reality is unknowable. It does not plunge us into darkness or confusion. Instead, it offers a more refined understanding. It tells us that knowledge comes in forms, in shapes, in balanced relationships. That to know something more precisely in one way is to accept a gentle loss of precision in another. And that this trade-off is not a flaw, but a fundamental feature of how the world is organized. This changes the goal of understanding. It is no longer about capturing everything at once, but about navigating these relationships with clarity and care. In a sense, the universe invites us to ask better questions. Not what is everything, but what can be known together and what must remain open. This is a quieter kind of inquiry, one that accepts limits not as barriers, but as guides. And when you begin to think this way, something interesting happens. The presence of uncertainty no longer feels like a loss. It begins to feel like space, room for possibility, for variation, for the unfolding of outcomes that are not rigidly fixed in advance. This perspective also reshapes how we understand prediction. In the classical dream, prediction meant certainty. Given enough information, the future could be calculated exactly. But in the quantum world, prediction takes on a different meaning. It becomes the ability to map probabilities with extraordinary precision. To say not exactly what will happen, but how likely each possibility is. And remarkably, this probabilistic framework is not weaker than classical prediction. In many cases, it is more powerful because it aligns more closely with how reality actually behaves. There is also a quiet humility embedded in this shift. The recognition that there are aspects of the universe that resist being fully pinned down. That no matter how far our knowledge extends, there will always be edges, regions where certainty fades into possibility. But this humility is not discouraging. It is, in its own way, deeply enriching, because it means that the universe is not a closed book, fully written and waiting to be read. It is something more alive, a system that retains openness at its core. And perhaps this is why the uncertainty principle continues to resonate beyond physics. It echoes a broader truth about understanding itself. That clarity does not come from eliminating all ambiguity, but from knowing how to move within it. That precision is meaningful not when it is absolute, but when it is balanced. That knowledge at its deepest level is not about control, but about relationship. If we return now to the question that has followed us from the beginning, whether uncertainty is a limitation or a design, we begin to see that the answer may not be one or the other. It may be both, depending on how we look at it. It limits certain forms of knowledge, yes. But in doing so, it also creates the conditions for structure, stability, and complexity. It prevents collapse, maintains balance, and allows the universe to exist in a form that can be explored at all. And so, the boundary that once seemed restrictive reveals itself as something quietly essential. A framework within which reality unfolds. A rule that shapes not only what we can know, but what can exist. As we prepare to move into the final part of this journey, we carry with us a new perspective. One that does not seek to remove uncertainty, but to understand it. To see it not as a gap, but as a feature. Not as an absence, but as a presence. Something that gives form to the very idea of knowledge. And in the next part, we will follow this idea outward into the larger universe, into stars, into technology, into the philosophical space where science meets reflection. We will see how this principle, born in the study of the smallest things, quietly shapes everything from the stability of matter to the limits of human understanding. For now, let the thought rest gently, that reality is not a fixed set of perfect answers, but a living balance between what is defined and what remains open. And that, in this balance, there is not only limitation, but a kind of quiet beauty. If you are still here, still listening, still drifting through this space between certainty and mystery, let me know by softly writing the number 2 in the comments. As we move into the final part of this journey, something begins to shift once again. Not in the principle itself, but in how far its influence extends. What began as a strange limitation in the behavior of tiny particles now reveals itself as something much larger. A quiet rule that does not stay confined to the microscopic world, but rises outward, shaping atoms, matter, stars, and even the limits of our most advanced technologies. And in doing so, it answers a question that has been gently building beneath everything we have explored. If uncertainty is real, if it is woven into the structure of reality, then where exactly does it matter? The answer is simple and at the same time astonishing. It matters everywhere. We have already seen how the uncertainty principle stabilizes the atom, preventing electrons from collapsing into the nucleus. But this is only the beginning, because once atoms exist, they combine. They form molecules, solids, liquids, all the structures that make up the physical world. And within all of these, the same balance continues to operate quietly in the background. Electrons do not settle into a single point or a single motion. They occupy regions, distributions, patterns that are shaped by the same constraints we have been exploring. This is why chemistry works, why bonds form, why materials have specific properties. Without the uncertainty principle, electrons would behave too rigidly, collapsing into the lowest possible energy state without structure or variation. The richness of matter would disappear. Even something as simple as the resistance of an object to being compressed, the feeling of solidity when you press your hand against a surface, is tied to this quantum behavior. As particles are pushed closer together, their positions become more confined. And as we now understand, this confinement increases the uncertainty in their motion, raising their energy and creating a kind of pressure that resists further compression. This is not just an abstract idea. It is part of what gives matter its everyday stability. The world feels solid because, at a deeper level, uncertainty is pushing back. And when we extend this idea further, we find it shaping some of the most extreme objects in the universe. Consider the life of a star. For most of its existence, a star balances two opposing forces. Gravity pulls inward, trying to compress the star. Nuclear reactions push outward, providing pressure that keeps it stable. But eventually the fuel runs out. The outward pressure weakens, and gravity begins to dominate. The star starts to collapse. In a classical universe, this collapse would continue indefinitely, crushing matter into an ever smaller space. But in our universe, something intervenes. As the particles inside the star are forced closer together, the uncertainty principle begins to assert itself. The confinement of particles increases their motion, raising their energy and generating pressure. In smaller stars, this pressure from electrons is enough to halt the collapse, creating what we call a white dwarf. In more massive stars, electrons are no longer sufficient, and protons and electrons combine to form neutrons. The collapse continues until neutron pressure, again rooted in the same quantum principles, provides resistance. The result is a neutron star, one of the densest objects in the universe. In both cases, the uncertainty principle is not just present. It is decisive. It determines whether a star stabilizes or continues collapsing. It shapes the structure of matter under conditions so extreme that classical physics alone cannot describe them. And so, the same rule that governs the spread of an electron in an atom also governs the fate of entire stars. This is what it means for a principle to be fundamental. It does not fade with scale. It does not weaken as systems grow larger. It remains quietly at work everywhere. And yet, its influence is not limited to natural systems. It also defines the limits of what we can build. In modern technology, especially in areas like quantum computing and precision measurement, the uncertainty principle is not an abstract concept. It is a practical constraint. Engineers designing sensitive instruments must account for it. When measuring extremely small distances or tiny changes in energy, they encounter a boundary, a point beyond which increasing precision in one aspect inevitably introduces noise in another. This is known as the standard quantum limit. But rather than seeing this as a barrier, scientists have learned to work with it. They create special states of light and matter that redistribute uncertainty, reducing it in one variable while increasing it in another. This allows them to push measurements beyond what would otherwise seem possible, all while respecting the underlying principle. It is a delicate balancing act, one that mirrors the deeper structure of reality itself. And so, as we step back and look at the bigger picture, a pattern becomes clear. The uncertainty principle is not an isolated rule. It is a thread that runs through everything, from the smallest particles to the largest cosmic structures, from the stability of matter to the limits of technology. It quietly shapes what can exist and what can be known. And this leads us gently toward the final question of our journey. Not just how the universe behaves, but what it means. If uncertainty is everywhere, if it defines both reality and knowledge, then what does that say about the nature of truth itself? As we continue drifting through this idea, the uncertainty principle begins to take on a quieter, more philosophical presence. No longer just a rule about particles or stars, but a lens through which we begin to see the nature of truth itself. Because if reality is structured in such a way that certain things cannot be fully defined together, then truth is no longer a single, perfectly sharp picture. It becomes something more layered, something that depends on perspective, on context, on the way we choose to ask our questions. In the classical world, truth feels absolute. Particle is here. It moves like this. It has a precise state that exists whether we observe it or not. Knowledge, in that sense, is simply the act of uncovering what is already there. But in the quantum world, that clarity softens. Not into confusion, but into something more flexible. A system does not present all of its properties in a single, unified form. Instead, different aspects come into focus depending on how we interact with it. This idea was once described as complementarity, the notion that certain features of reality cannot be fully expressed at the same time, but are both necessary for a complete understanding. You can see one aspect clearly or another, but not both with perfect sharpness. And yet both are real. Both are part of the whole. It is not that one is true and the other is false. It is that truth itself is distributed across these different perspectives. This may sound abstract, but it has a surprisingly simple feeling when you sit with it. Imagine trying to describe a complex object using only a single viewpoint. From one angle, certain details stand out clearly. From another, different features emerge. No single perspective captures everything. And yet, each perspective is valid within its own context. Together, they form a more complete picture, even though no single image contains it all. The uncertainty principle brings this idea into the heart of physics. It tells us that some aspects of reality are not just difficult to measure together. They are not defined together in a perfectly sharp way. And so, our descriptions must reflect that. We do not lose truth. We learn that truth has structure, that it comes in pieces that must be understood in relation to one another. This shift has deep implications not only for science, but for how we think about knowledge more broadly. It suggests that seeking a single, final, all-encompassing description of reality may not be the right goal. Not because reality is incomplete, but because completeness itself may not take the form we expect. Instead of a single perfect map, we may need multiple maps, each revealing different aspects, each shaped by the limits and relationships we have been exploring. And yet, this does not lead to relativism or the idea that anything can be true. The structure imposed by the uncertainty principle is precise. It sets clear boundaries. It defines exactly how different aspects are related and how their uncertainties must balance. There is still a deep order to the universe, but it is an order that allows for multiple complementary views, rather than a single totalizing one. As scientists have come to accept this, the role of the observer has also been reinterpreted. Not as someone who creates reality, but as someone who participates in shaping the conditions under which certain aspects become defined. The questions we ask, the experiments we design, the variables we choose to measure, all of these influence which features of a system come into focus. This does not mean reality is subjective. It means that our access to reality is structured, guided by the same principles that govern the systems themselves. And in this way, the uncertainty principle gently dissolves a long-standing illusion. The idea that we stand outside the universe, looking in, capable of describing it completely without being part of it. Instead, we are embedded within it. Our knowledge is not detached. It is woven into the same fabric, subject to the same limits, shaped by the same relationships. This realization can feel humbling, but it is also deeply grounding. It reminds us that mystery is not a sign of failure. It is a natural consequence of the way reality is organized. That the edges of knowledge, the places where certainty softens, are not gaps to be eliminated, but boundaries that define the landscape of understanding. And as we move closer to the final segments of this journey, something begins to settle. The uncertainty principle is no longer just an idea to be explained. It becomes something to be experienced, a quiet awareness that the world is not fully fixed, not fully open, but balanced between the two. A place where knowing and not knowing coexist, not in conflict, but in harmony. As we move deeper into this quiet understanding, the uncertainty principle begins to feel less like a boundary we encounter, and more like a rhythm that reality follows. A pattern of balance that repeats itself across different scales, different systems, different layers of existence. And what becomes increasingly clear is that this balance is not accidental. It is not a side effect. It is a condition that allows complexity, structure, and even experience itself to emerge. Because imagine, for a moment, a universe without this balance. A universe where every property could be defined with absolute precision at all times. Every particle fixed, every motion exact, every interaction perfectly determined. At first, this might sound like the ultimate clarity, a world without uncertainty, without ambiguity. But if you follow that idea carefully, something strange begins to appear. In such a universe, change would lose its softness. Transitions would become rigid. Systems would have no room to fluctuate, no space to explore possibilities. Everything would unfold like a perfectly wound clock, each moment locked into the next with no variation. And in that kind of universe, something important would be missing. The ability for structures to stabilize through balance. The ability for systems to adapt, to respond, to exist in states that are not perfectly fixed but dynamically sustained. The uncertainty principle, in contrast, introduces just enough openness to allow these behaviors. Prevents extremes. It ensures that no system can collapse into absolute rigidity or absolute localization. It maintains a kind of dynamic equilibrium where definition and flexibility coexist. This becomes especially meaningful when we consider the emergence of complex systems. From molecules forming intricate chemical structures to biological systems maintaining delicate internal balances, to even the processes within our own brains. All of these rely, in some way, on a world that is not perfectly rigid. A world where probabilities, fluctuations, and distributions play a role. While these larger systems are not directly governed by quantum uncertainty in an obvious way, the foundation they rest upon is the stability of atoms, the behavior of electrons, the interactions that give rise to chemistry. All of it traces back to the same principles we have been exploring. And so, uncertainty becomes part of the deep architecture that allows the universe to build itself upward into complexity. Not by removing structure, but by shaping it. Not by introducing randomness without form, but by creating a framework where possibilities can exist within limits. There is also something quietly profound about how this principle shapes our interaction with knowledge itself. Because as we have seen, the uncertainty principle does not prevent us from knowing. It guides how we know. It tells us that knowledge is not about capturing everything at once, but about choosing where to focus, understanding the trade-offs, and working within the structure that reality provides. In modern science, this idea has become deeply integrated into how experiments are designed. Physicists do not attempt to eliminate uncertainty. They work with it. They prepare systems in ways that highlight certain properties while accepting the necessary blur in others. They use techniques that redistribute uncertainty, concentrating it where it matters less and reducing it where precision is needed. This is especially evident in fields like quantum optics and quantum computing, where the control of uncertainty is not a limitation, but a resource. Even in our most sensitive instruments, such as those used to detect gravitational waves or measure incredibly small changes in energy, the uncertainty principle sets a fundamental limit. But rather than stopping progress, it defines the playing field. It tells us how far we can go and how we must adjust our methods as we approach that boundary. And in this way, the principle becomes something almost elegant. A rule that does not simply restrict but organizes. A guide that shapes both the behavior of systems and the strategies we use to understand them. But perhaps the most subtle shift it brings is in how we relate to the unknown. In the classical view, the unknown is something temporary, a gap that will eventually be filled, problem to be solved. But in the quantum view, some aspects of the unknown are not temporary. They are structural. They are part of the way reality is built. This does not mean we stop asking questions. It means we ask them differently, with an awareness that some answers will come with trade-offs. That clarity in one direction may require openness in another. That understanding is not about eliminating all uncertainty, but about navigating it with insight. And as this realization settles, the uncertainty principle begins to feel less like a limitation imposed on us, and more like a quiet invitation. An invitation to explore a universe that is not fully fixed, not fully open, but balanced between the two. A universe where knowledge has edges, and those edges are part of what makes it meaningful. As we begin to approach the end of this journey, something subtle starts to unfold. A kind of quiet reconciliation between what we once expected from reality and what reality actually offers. Because at first, the uncertainty principle can feel like a loss, a removal of something we thought we could have: perfect knowledge, complete precision, total control. But now, after moving through its deeper layers, it begins to reveal itself differently. Not as something taken away, but as something that was never meant to exist in the way we imagined. The idea of a perfectly knowable universe is deeply human. It reflects a desire for certainty, for clarity, for a sense that everything can ultimately be understood without ambiguity. And for a long time, it seemed as though science was moving steadily toward that goal. Each discovery sharpening the picture, each equation refining the map. But what the uncertainty principle shows us is that this picture was never meant to become perfectly sharp in every direction at once. That the very act of sharpening one part of reality inevitably softens another. And instead of seeing this as a flaw, we can begin to see it as a kind of balance, a built-in moderation that prevents reality from becoming too rigid, too fixed, too constrained. Because a universe with absolute precision everywhere would not just be predictable, it would be frozen in a certain sense. Every detail locked in place, every possibility already resolved. There would be no room for variation, no space for emergence, no openness for systems to evolve in the way they do. The uncertainty principle gently prevents this. It ensures that there is always a degree of openness, a softness at the edges of definition. Not chaos, not randomness without structure, but a controlled flexibility. A way for systems to exist in states that are stable, yet not rigidly fixed. This is what allows atoms to form stable regions rather than collapsing into points. It is what allows energy to distribute in ways that create patterns, structures, and interactions. It is what allows the universe to breathe, in a sense, to maintain both form and possibility at the same time. And this idea extends beyond physics into something more reflective. Because when we think about knowledge itself, we often imagine it as something that can be completed, a final understanding where nothing remains uncertain. But the uncertainty principle suggests that this completion may not be possible in the way we expect. That knowledge is not a closed structure, but an open one. A system where each increase in clarity reveals new relationships, new balances, new edges. This does not make knowledge weaker. It makes it more dynamic, more alive. It means that understanding is not about reaching a final endpoint, but about continually refining how we navigate the relationships between different aspects of reality. It becomes less about control and more about alignment, less about eliminating uncertainty and more about understanding its role. And in this way, the uncertainty principle quietly reshapes our relationship with the unknown. Instead of seeing it as something to be conquered, we begin to see it as something to be explored. Not a void, but a space filled with structure, with rules, with meaning. A space that is not empty, but simply not fully defined in every direction at once. There is also a kind of calm that comes with this realization, because the pressure to know everything, to resolve every detail, begins to ease. We see that some aspects of reality are not meant to be fully pinned down, and that this does not diminish our understanding. It gives it form, it sets its boundaries, it tells us where clarity lives, and where openness remains. And perhaps this is why the uncertainty principle feels so enduring. Not just because it is scientifically correct, but because it resonates with a deeper pattern. A pattern where balance is more fundamental than extremes, where structure and flexibility coexist, where knowledge and mystery are not opposites, but partners. As we move into the final segment, we will let this idea settle into something quieter, a slower reflection, not on equations or experiments, but on what it feels like to exist in a universe shaped this way. A universe where certainty has its place, but so does uncertainty, and where both are necessary for the story to unfold. And now, as everything begins to slow, we arrive at the quiet edge of this journey. Not at a conclusion in the traditional sense, not at a final answer that resolves every question, but at something softer. A place where understanding and mystery sit gently beside one another, no longer in conflict, but in balance. The uncertainty principle, which once may have felt like a limitation, now reveals itself as something far more subtle. A quiet shaping force. A rule that does not close the universe, but keeps it open in just the right way. It allows structure without rigidity, knowledge without finality, clarity without removing the possibility of wonder. And perhaps this is where its deepest meaning begins to emerge. Not in the equations, not in the experiments, but in the way it changes how we see the world. Because when you accept that not everything can be known at once, something shifts. The need for total certainty begins to loosen. The expectation of a perfectly sharp reality softens. And in its place, there is room for curiosity, for reflection, for a kind of calm that does not depend on having all the answers. If you imagine the universe as a vast landscape, the uncertainty principle is not a wall that blocks your path. It is more like a horizon, a boundary that moves with you, always present, always defining how far clarity can extend at any given moment. You can walk toward it, refine your view, sharpen your understanding, but it never disappears. And yet, it does not need to, because everything meaningful happens within that space. Within that space, atoms form and hold together. Within that space, stars live and evolve. Within that space, thoughts arise, questions form, and understanding grows. The horizon does not limit these things. It gives them context. It gives them shape. And so, what once seemed like a restriction becomes something almost protective. A way of ensuring that reality is not reduced to something overly rigid or completely predetermined. A way of preserving a subtle openness, a quiet flexibility that allows the universe to remain dynamic, responsive, alive. There is also something deeply human in this realization, because our own experience of the world is never perfectly sharp. We do not hold every detail at once. We focus, we shift, we see certain things clearly while others fade into the background. Our understanding is always partial, always moving, always shaped by where we place our attention. And in this way, we are not separate from the principle we have been exploring. We are part of it. The limits of knowledge are not just out there, in distant particles or faraway stars. They are here, woven into the way we perceive, the way we think, the way we engage with the world. And rather than diminishing our experience, these limits give it texture. They create contrast, depth, and the possibility of discovery. Because if everything were already fully known, fully fixed, there would be nothing to explore. No questions to ask, no paths to follow, no sense of unfolding. The presence of uncertainty is what allows the journey itself to exist. And so, as you rest with this idea, you might begin to feel it less as a concept and more as a quiet atmosphere, a background presence that shapes everything without demanding attention. A reminder that knowledge and mystery are not opposites, but companions. That clarity does not require completeness. That understanding does not eliminate wonder. The universe, in this sense, is not withholding itself from us. It is offering itself in a form that cannot be fully captured all at once. A form that invites exploration, that rewards attention, that reveals itself gradually, always leaving a little more beyond the edge. And maybe that is enough. Maybe it is enough that we can know something, even if not everything, that we can trace patterns, understand relationships, glimpse the structure beneath the surface, while still allowing space for what remains open. Because in that openness, there is a kind of quiet beauty, a sense that the story is not finished, that there is always more to discover, more to feel, more to understand. So as the mind begins to settle and the details gently fade into the background, you can let this final thought linger, not as a question that needs answering, but as a feeling that can simply be held. That reality is not a fixed, perfectly defined object, but a balance. a delicate interplay between what is known and what remains just beyond reach. And in that balance, the universe becomes not smaller but deeper, not more certain but more alive. If you are still here, still listening as the edges of this journey soften into quiet, let me know by gently writing the number 3 in the comments.